Hello and welcome to the theory prep video on implications and equivalences. Let's get right into it. First, what is an implication? An implication is a mathematical proposition of the form if P, where P are some conditions, then Q, where Q are some conclusions. And although this might seem a little bit cryptic at first because P and Q are just symbols, I bet you've seen a lot of implications before. For example, the quadratic formula. The quadratic formula can be written as if we have some quadratic equation that's equal to 0 and A is not equal to 0. A not equal to 0 just means that this is an actual quadratic equation, not some linear equation, then x must be equal to this value here. And if you think back to how you use the quadratic formula, you used it to find the zeros of a quadratic equation, which is exactly what this is saying. It's saying that if you have a quadratic equation that's equal to 0, then x must be of these values. So therefore, you can use those values as the zeros of x, or the zeros of the equation. So another example that you might have seen in geometry is, let's say you have two triangles, you have some triangle ABC, and then you have some other triangle, DEF, and you know some things about them. For example, you know that AB is equal in length to DE, and BC is equal in length to EF, and then the angle between those two sides is the same thing. Well, then this implies that the triangles are congruent. So again, that's an implication, right? Because if you know some certain properties about the sides and the angles, then you can conclude a congruency statement about the triangle. So this is a pretty common form of proposition in math. If some stuff, then some other stuff. And it's really nice to work with. So we should know how to prove these facts. But before we get to the proof technique, let's just talk about a couple different ways people write an implication, because there's lots of different ways people will notate it. So there's what we discussed, which is if P, then Q. Sometimes people use this arrow, which is just mathematical shorthand, like for all or there exists. Sometimes people will use implies, which is basically just a synonym. Another thing people will write is Q if P. Now, importantly, Q and P are swapped here, and that's because, well, if you move the if, then English grammar dictates you should move where the conditional is. And last thing people will write is P only if Q. And there's a lot of different things people will write, and so if this is a little bit confusing, I think it's helpful to see an example. So I wrote this out with an example implication if you want to pause here and just sort of think about these for a little bit. Great. So let's do a proof of an implication. And actually, we've already done one. If you remember in the first video, we said if n and m are even integers, then their sum is even. So here, this is P and this is Q. And this suggests a general formula for how to solve implications. The first step is you assume P. And the second step is that you prove Q. And obviously this is a really high-level strategy, but that's because proving Q can happen a lot of different ways. When we did this proof, we used the proof of a universal statement. Next week, we might use proof by induction to prove Q. And so there's a lot of different ways that you might prove it, but the important part is you should always assume the hypotheses. You should always assume P first. And if you think back to the proof that we did that. The first thing we did was we assumed that n and n prime are even, right? So we assumed the hypothesis of the statement. And then the second thing was we proved that their sum n plus n prime is also even. And so in general, whenever you have an implication, the first thing that you should do is assume the first part, assume the if, and then prove the then. Great. So let's do an actual proof of implication, because I think that will be instructive. First, a quick definition. An integer n is odd if it can be written as 2m plus 1 for some m, which is an integer. And again, whenever you see a definition, always think, does this make sense to me? Does this have the properties that I think it should have? And in this case, maybe a good thing to check is, intuitively to me, a number should not be able to be both even and odd. So that would be a good thing to check. You should check that you can't have a number that's both even and odd. And I think this is actually a pretty instructive proof, because we're going to learn this technique called contradiction, proof by contradiction, in this video. And I think you can do a pretty clean proof by a contradiction that a number can't be odd and even at the same time. So it'll be helpful to sort of review. Great. So what theorem are we going to prove? We're going to prove that if n is an integer and n squared is even, then n is also even. So let's follow our proof technique. Remember, the first step is always assume P. So in this case, we assume that n squared is even. And now we want to prove the second part. And to prove the second part, well, we're going to proceed by contradiction. So what is a proof by contradiction? In a proof by contradiction, we take the statement we are trying to prove and we assume that it's false. So in this case, we would assume that n is odd. We then use that to derive a contradiction or something that's impossible, something that cannot be true. And that implies that our initial thing that we assumed must actually be true, because if it's false, it produces a contradiction, which like definitionally cannot be true. So in this case, we're going to assume that n is odd, right? We're going to assume that this is wrong. Then we're going to use that to imply that n squared is odd, which will contradict our initial assumption or our hypotheses that n squared is even. And therefore, we know that this second statement, n is even, must be true. Let's write it out. We often write suppose towards contradiction to indicate to the reader that we are going to proceed by proof by contradiction. And here, we're going to suppose towards contradiction that n is odd. Then by definition, we can write n as equal to 2m plus 1 for m, an integer. And then that means that we can write n squared as equal to 2m plus 1 squared, which is equal to 4m squared plus 4m plus 1, which we can rewrite as 2 times 2m squared plus 2m plus 1. And since m is an integer, 2m squared plus 2m is an integer, which means that this number, n squared, is odd. That produces a contradiction because we assume that n squared was even, and therefore our initial assumption that n is odd must be wrong, and therefore n must be even. So that completes the proof. Proof by contradiction can be a little confusing, so let me go over the sort of fundamental ingredients one more time. First, you assume the thing you're trying to prove is wrong. Then you reach some sort of contradiction or impossibility. Thus, the thing that you are trying to prove must be right. Great. So let's talk about equivalence, or if and only if. A lot of times in mathematics, you'll find that two constructions or two conditions that you have are equivalent. I think a useful way to think about this is they're like synonyms in the English language. Like you could just switch one for another. You know, if you can say certain things about a triangle, then you just switch that and you just say certain other things about a triangle because those conditions are exactly the same. And that's a really useful mathematical tool when you're doing proofs. It's also a really cool result because it says, wow, these two conditions that I don't know if they're that related, they're actually the exact same thing. So these are pretty important results in math. And we often say, like P is equivalent to Q, or P if and only if Q in that case. Sometimes we abbreviate as if with two F's to indicate if and only if. So let's give some examples of if and only if statements, because I think that will help make it a little bit more concrete. So the first one, again from geometry, is if you have two triangles, have the same side lengths, if and only if they have the same angles and one side length is the same. So that means that these two conditions are the same. If two triangles have the same side lengths, then they have the same angles and one side length is the same. Or if two triangles have the same angles with one same side length, then that means all three of their side lengths are the same thing. Like anytime you can say one of these things about triangles, the other one is immediately true. And the second example that I provide is maybe from linear algebra. So if you have some matrix A, it's invertible, if and only if ax equals 0 has only the trivial solution x equals 0. So this second term is like, you know, you can't multiply pre-multiply some non-zero vector by a and get 0. So again, this is really cool, right? Because it gives two conditions on the matrix that are exactly the same. You know, if you need to substitute them in proofs anywhere, you can do it in either direction. And also, it's nice to know that these are exactly characterizing the same matrices. Great. So I think one more thing that's helpful to think about in terms of if and only if is to break it up, because it does break up into two parts. So if we say P, if and only if Q, there's two parts here. There's the only if part and there's the if part. And so the if part is P if Q, right? And the only if part is P only if Q. And as we discussed earlier, P only if Q is the same thing as P implies Q. And here, as we discussed earlier, P if Q is the same thing as Q implies P. So really, when we say like if and only if, what we mean is that, you know, the first thing implies the second thing and the second thing implies the first thing. And this suggests maybe another notation that we can write this with. Sometimes people will write P and then an arrow in both directions, Q, which means like P implies Q and Q implies P. So there's two directions to an if and only if statement. And that will help us when we're sort of trying to do the proof. Great. So how do we prove an if and only if statement? Let's start with a quick definition because we're going to be talking about primes in this proof. So a natural number P greater than 1 is prime if it is not divisible by positive integers other than 1 and itself. Again, make sure that makes sense to you. Is this what you normally think of as a prime? Now, the theorem that we're going to prove is that P is prime. So that's the first part. If and only if P is not divisible by any other primes. Remember, whenever you see an if and only if statement, you want to prove both directions as we outlined. You want to prove that the first thing implies the second thing implies the first thing. And we'll often refer to P is prime implying P is not divisible by any other primes as the forwards direction, because you're going forward in this statement, and proving the other direction using P is not divisible by any other primes to prove that P is prime as the backwards direction. So I've written those out more clearly here. The forwards direction says if P is prime, then it is not divisible by any other primes. And the backwards direction says if P is not divisible by any primes that are not equal to it, then P is prime. So if we prove both of these things, then we'll have proved the theorem. Let's prove the first direction. If P is prime, then it is not divisible by any other primes. Well, remember, by definition, if P is prime, it's not divisible by anything other than 1 and itself. And 1 is not prime. And P itself is not an other prime. So that means that we know P is not divisible by any other primes. This is sort of a direct implication of the definition of P being prime. Now let's prove the backwards direction. Again, with any implication, remember the first step is to assume P. So here we're going to assume P is not divisible by any prime Q not equal to P. And now we must prove P is prime. We can do this by contradiction. So suppose towards contradiction that P is not prime. So n, there's some number n that's not equal to 1, and that's not equal to P that divides it. And when we say n divides P, what we mean is that P is equal to n times m for some m in the integers. That's what it means to divide something. Then we want to reach a contradiction. So because of this, we can use the fundamental theorem of arithmetic, which basically just says you can take any number and write it as the product of unique primes up to reordering. So basically it just says we can write n as the product of primes. And that's intuitive result, right? Like you could write 6 as the product like 2 times 3, or 9 as the product of 3 squared. So that means that we can write P as equal to some prime Q1, some prime Q2, all the way through Qi. Let's say if I primes multiply to n by the fundamental theorem of arithmetic, and then times m. But that implies that Q1 divides P, because we can write P as Q1 times this, which is some integer, right? Because the product of integers is an integer. And that means Q1 is prime and divides P. So we also just want to check that Q1 is not equal to P, but we know Q1 is not equal to P because n was not equal to P, right? And so in particular, n must be smaller than P, since you multiply by some other integer to get P. And then by the fundamental theorem of arithmetic, we broke it up into a bunch of primes, which are all smaller than that. So that means that Q1 is smaller than P, so it can't be P. So we found some other prime that's not equal to P that divides it. And that's a contradiction with our first assumption. Thus, when we assumed P was not prime, that fact must be false. So P must be prime. And that completes the proof of the backwards direction. So again, whenever you have an if and only if statement, you should break it down into each component direction, and you can use different proof techniques to prove either one.